We now discuss the final selection step of the stepwise of the selection methods. This final selection step is shared by best subset selection and also by the forward and backward stepwise methods. By the way, I would add that there is also the possibility of introducing forward-backward methods in which not only you can have forward or backward steps, but in the same method you could move both forward and backward depending on the chances to improve your performance, the performance of your model. But for our purposes, it is okay to consider just forward and backward. This just to know that you could find in the literature also methods under the name of forward-backward stepwise regression. But now we must face the final step when we have candidate models of different complexity and we have to choose the best one. We have already seen that R squared is not a good method because it will favor always the most complex model. So we need alternative techniques. And there are two possible approaches. Okay, we can indirectly estimate the test error by adjusting the training error in order to account for overfitting. So we start from the training error, but we introduce some adjustments in such a way to penalize models that are overly complex. And the idea is that these adjustments should help estimating the test error through a correction made on the training error. There is a second approach in which we directly estimate the test error using validation or cross-validation that we have already discussed in the previous chapter on resampling. We illustrate both techniques next. So, methods that fall in the first category are CP, AIC. AIC stands for Archaic Information Criterion, BIC, Binary Information Criterion, and adjusted R squared. So these techniques adjust the training error and they give you indicators that you can minimize or maximize because CP, AIC, BIC are to be minimized while adjusted R squared is to be maximized. And first of all, let's see how they work on our credit dataset. Okay, in the credit dataset we show CP, BIC and adjusted R squared. So remember that CP and BIC are to be minimized while adjusted R squared is to be maximized. So we see that when the number of predictors is small, CP is large, then it goes down and you have a minimum in 6 for 6 predictors. BIC instead has a minimum for 4 predictors, so it suggests the use of a less complex model, while adjusted R squared has a maximum in correspondence of 6 predictors. You can also see that all the 3 methods are quite flat around the minimum, so they give a suggestion, but they also tell you that in this case there is a range of models that are more or less equivalent, so it will not be much different to use 5 or 7 or 6 or even 4 parameters. The other thing to be considered is that they can give different suggestions. So BIC suggests 4, but CP suggests 6, and 6 also is the suggestion by adjusted R square. square. So this is something that you should consider. So you might use more than one criterion and then see if they agree or if there is a disagreement. And in that case, you could choose based on some other criterion what is the model you would like to use. But now let's give some details on these criteria. So CP, which is also known as malus CP, has this expression. So it is 1 over n RSS, residual sum of squares. Okay, and then you add this term, which is twice d. D the total number of parameters. So if you have p parameters and the intercept, it will be d equal p plus 1, and sigma hat squared. Sigma hat squared is an estimate of the variance of the error associated with each measurement. And okay, now here there is the problem that in many cases you do not know sigma squared, so you will have to estimate it. And this is something that we will discuss in the next lecture. So for the time being, you just can believe that we have methods to get an estimate for sigma squared that we call sigma hat squared. So here you plug your estimate of the measurement error. After all, this could be regarded as a measurement error, twice the number of parameters, and this is the usual RSS in the training data. The idea that we will choose the model that achieves the smallest CP. The AIC criterion, on the other hand, is defined based on the maximum likelihood. So you consider the maximized value of the likelihood, which is called capital L, and then this is minus 2 the logarithm of L plus twice d, where d is the total number of parameters. So this is associated with the estimation performed by likelihood maximization. But if you have a linear model with Gaussian errors, you can show that likelihood maximization is equivalent to least squares, and in that case you can see that this minus twice the logarithm of L has to do with the residual sum of squares, and in the end you can prove that this for the case of linear models with Gaussian errors is equivalent to malus CP. So they just give the same answer. They are the same in that case. But when you do not have a linear model and nevertheless you can compute the likelihood, AIC gives you a more general criterion that can be applied every time you can define a likelihood on your data. Okay, finally some details on BIC. BIC is 1 over n, the residual sum of squares, plus log of n, the logarithm, times d, times sigma hat squared. This is the usual estimate of the variance. And again, the idea is that this is an estimate of the test error, and therefore we will select the model with the smallest BIC. Please notice that BIC is not that different from CP, so you can see that they are quite similar. The difference is that here you have 2, and here you have the logarithm of n. And the logarithm of n is greater than 2 whenever n is greater than 7, whenever n is greater than 7, which is of course quite usual. So you are not going to estimate models having as few data as 7 usually. Okay, from time to time it can occur, but it will something quite exceptional. Therefore, in most cases, BAC will have here a number, log of n, which is greater than 2. Therefore, the penalty on the complexity of the model is heavier, and as a result, BAC is going to select more parsimonious models, so models with fewer parameters, and this is something that you can appreciate in this figure. As a matter of fact, if you compare CP and BAC, you can see that BAC suggests 4 predictors and CP suggests 6. So as a matter of fact, this confirms our observation. Okay. All right, finally, we have adjusted R squared, and adjusted R squared is a modification of the R squared statistics, which is defined as R squared equal to 1 minus RSS over TSS. RSS is the residual sum of squares associated with your model, and TSS is the total sum of squares, that is the residual sum of squares associated to the null model, where you just have the intercept. So you compute the sum of squared residuals when you just have the intercept, so the mean value. And you take the ratio with the residuals that you have when you are fitting your model. Okay, usually you just have 1 minus RSS over TSS, but if you adjust the usual R-squared statistics and you introduce the new adjusted R squared, you are dividing this RSS by this term, and you divide TSS by this other term. And an easy way to remember is that this is, I think that this is P, because this is the number n minus the total number of parameters. So if you have P predictors, the number of parameters will be P plus 1. So you are computing n minus parenthesis P plus 1, close parenthesis. And here you have n minus 1 because the number of parameters in this case is 1, because you just have the intercept. Okay, and the idea is that the R squared will be maximal when you consider the full model, for instance, a very complex model, because with more parameters you have more degrees of freedom, you fit better the data, and so the residual sum of squares is going to decrease and R squared is going to increase. But if you introduce this adjustment, you can see that when you increase the number of parameters, this denominator becomes small, because this d minus 1 or p minus 1 approaches n, and then you divide by a small number, this term becomes large, and so you are no more guaranteed that the most complex model will have the best R squared. So in this case, RSS is going to decrease as the number of variables increases, but the presence of these terms in the denominator at some point will have this ratio to increase, and therefore we find that R squared is expected to have a maximum, and the maximum is the one that indicates as the model to be selected. This is something that we can see here. So at the beginning you have an increase, and then at some point you reach a maximum, and that is where you find your model. And the difference, as I already said, with respect to the R squared statistic is that the adjusted R squared pays a price for the inclusions of unnecessary variables. So if you include a variable that does not reduce RSS, anyway this variable is going to reduce this denominator, and therefore it is increasing the ratio of RSS over this term, and therefore it is reducing the value, because there is the minus, it is reducing of the adjusted R squared. The final method to assess and compare our models of different complexity is by means of validation and cross-validation. And we know that we have a sequence of models to be compared, and we would like to find the best order. Okay, and we can do this using validation or cross-validation, and we compute the estimated test error by validation, by cross-validation, or by validation or cross-validation, and then we select amongst the models MK with K from 0 to P, we select the one that has the best, the smallest test error as estimated by validation or cross-validation. What's the advantage of using validation and cross-validation is that we directly go for obtaining an estimate of the test error, and perhaps more importantly, you do not need an estimate of the error variance. So we have seen that in BIC and CP, in AIC there is also the issue of the likelihood, but in the likelihood you have to plug the variance. So these criteria need an estimate of the error variance. Okay. Therefore, the applicability of validation and cross-validation is wider, because another issue could be that for not in the linear regression, but these problems we are addressing arise also with other types of models, and in some cases it is also difficult to be sure about the degrees of freedom of the model. So we have used D in this case as associated with the number of coefficients to be estimated, but for our models we say that D is the degrees of freedom of the model, but while in a linear model it is very clear what the degrees of freedom are, so you just count the number of the unknown parameters, the number of unknown parameters. In other more complex models it could be not so clear what the degrees of freedom are, and so in this case application of AIC, BIC, SCP could be troublesome. And on the contrary, you can use validation and cross-validation without any problem. Okay, let's see how it works on credit data examples. So here I have BIC. Okay, this is the square root of BIC, which is also an estimate of the standard deviation of the test error, and this is the same quantity estimated by validation and cross-validation. And okay, we already know about the suggestion that is made by BIC. This is what you find when you apply validation, and in this case you have a minimum for 6 predictors, and this is what happens when you have cross-validation. In this case, again, you have a minimum for 6 predictors. Some details, the validation errors, so we have validation and cross-validation. Now, the validation errors were computed by randomly selecting 3/4 of the observations that were used as training set and reserving the remaining 1/4 of the data as validation set. Concerning cross-validation, instead, we used a tenfold scheme. This means that we performed the estimation 10 times. Every time we were keeping apart 1/10 of the data and using 9/10 for training. After having estimated the model, we try to predict the data that were kept apart. Okay. We have just seen that in this example, validation and k-fold cross-validation suggested the same model. Nevertheless, and this was something that you already observed before when using the criteria BIC, AIC adjusted R squared. You can see that there are a number of models that are roughly equivalent, so their indexes are not so different from each other. Therefore, the issue arises of selecting the number of predictors when you do not have a clear-cut response. And for this purpose, there is a practical rule that we call the one standard error rule. And if you are using validation or cross-validation, especially this is good for k-fold cross-validation, you calculate the standard error of the estimated mean square error on the test data, and you make this calculation for each model size, and then you are not using the model order that minimizes k-fold cross-validation, but you just select the smallest model such that its test error is within one standard error of the lowest point in the curve. So let's go back. Let's go back here. So this is the minimum point. Okay, you can see. And since you are performing k-fold cross-validation, you can also have an estimate of the standard error of this validation error, and you just consider a band such as +1 standard error, -1 standard error, and then you are selecting the smallest number of predictors such that the cross-validation error is within this band. What's the rationale? The rationale is that we like validation and cross-validation, but we should be aware that the result is a random variable because they are based on the data. So depending on how you split the data in training and validation, and depending also on the data that were sampled, you must be aware that your cross-validation error is an estimate of the test error. As such, it could be wrong. So if you choose the number of predictors that minimizes the cross-validation error, you are going to make a random choice, and especially when the curve is very flat, this is a flat curve with random values, it will happen that your estimate could be uncertain, and you could, by pure chance, choose a model that is quite complex or more complex than necessary. Our idea is that given that the test error is about the same, I prefer a simpler model. So if the test error is not to change very much, I will prefer a simpler model to a more complex one. So the idea is I take the minimum, I construct confidence bands, but these are confidence bands just +1 standard error, -1 standard error, and then I go on the left and I choose the simplest model such that its performance is within the band. Being within the band means that it is not so different from the best performance, which is estimated, after all, the estimated best performance that I have found, and moreover, it has the advantage of being a simpler model. Okay, I think we can stop here. Thank you.